All right, welcome everyone. Thank you for joining us today for the University of Texas Energy Symposium. I'm Kerry King, Assistant Director and Research Scientist at the Energy Institute here at the University of Texas. We're proud to host this weekly symposium. Clicker here, my intro slides. Before I introduce today's speaker, I'll just give an idea of who's coming up in the next couple of talks. So we've got two carbon dioxide talks, capture talks in a row, if you will. So next week will be carbon capture and storage talk from the sort of global perspective from Tim Dixon, who is the program manager, general manager of the greenhouse gas program at the International Energy Agency. And then October 1st, we'll have someone here from our own campus, Swadesh Mahajan. He's a research professor, and he's going to tell us about fusion. He's part of a fusion startup company, and this is part of his research he studies. So we're going to have a local talk on fusion. Oops, sorry. Today, it's my pleasure to introduce Fred Klossman. He's a research associate now at the Makeda Department of Chemical Engineering. I'll give you a little bit of a background on him. So he's had a career in industry before coming here to the University of Texas. So he had a variety of roles through his career before joining the chemical engineering department here. And here he directs laboratory work related to carbon dioxide capture with alkylamine solvents. All right, didn't ask that beforehand. So he works closely with people at the separations research facility that's here on campus, or here at the northern campus at J.J. Pickle, Gary Rochelle, and others. Before he came back here, he worked at Phillips 66 in the CO2 capture and avoidance group. And then after that, he worked as the director of cracking research with Phillips 66. So, and again, he works here now with Dr. Gary Rochelle and others to study CO2 capture at power plants. And so his talk today is going to give us some insights into the latest, or the trend and the latest challenges in CO2 capture with these amine solvents. So this method, or the method of capturing CO2 from gases, has been known since the 1930s. He'll give us a little breakdown on that. But through improved amine selection, or piperazine, an advanced process flowsheet, UT has improved on the first generation of CO2 capture over the course of research here at the University of Texas. This is important to lower the cost and to de-risk CO2 capture with pilot programs here at our separations research program facility, as well as the National Carbon Capture Center in Wilsonville, Alabama. That's part of Southern Company, so they're relatively unique in having a research program as part of an electric utility, and so it's nice to have a partnership there. And so his talk, he's going to tell us about the barriers to deployment of CO2 capture with amines and discuss UT's efforts to address these challenges through technological improvements. So with that said, let's welcome Dr. Fred Klossman.
Great. Okay. Thank you, Kerry. My talk today is called Lowering the Risk of Commercialization of CO2 Capture with Amine Solvents. I'm going to ask that you hold your questions towards the end, because I think a lot of times my slides have a leading thought. In the next slide or two, you might actually get your question answered. Nevertheless, I'll leave plenty of time for questions. I'm going to cover top conclusions from this talk. I'm going to go into the background and brief history of CO2 capture, referencing a patent from 1930 for produced gas treatment to remove sour gas components, including H2S and CO2. I'm going to give you an overview of UT's process for CO2 capture using piperazine. I'm going to talk about process improvements that we've implemented and that are analogous to what you would see in other industry processes that compete with us. I'll talk about the barriers and risks to CO2 capture with amines. Now, I want to pause and make sure you understand, this is only about CO2 capture. So a lot of times we talk about CCS or CCUS, being carbon capture, utilization, and sequestration. Today, I will not be talking about sequestration or utilization. Other folks work on that at University of Texas. I'm going to reference a feed study at the Mustang station in West Texas. This is front-end engineering design. And I'm going to do that so that I cover the costs of CO2 capture as we know them. I'm going to talk about solvent degradation and oxidation as a barrier to implementation of this solvent and how we've gone about trying to solve that problem. I'll talk about emissions and reclaiming, and that will kind of lead back to the oxidation issue, and then I'll go through those conclusions again. So what are our top conclusions that if you want to leave in the next 5 minutes, just look at this slide and you can walk out and you can claim you learned the top important things here today. The cost of capture is about $168 per metric ton of CO2. And I've referenced here at an IRR of 10% and a load factor of 52% using the Mustang station front-end engineering design as our reference case from 2022. That was a very rigorous cost workup. And it's driven largely by CAPEX, very large CAPEX items. Another barrier or risk is amine losses. These can be partially mitigated through flue gas impurity removal. I'll talk about a couple of strategies for that. And emissions. This can also be partially mitigated through those impurity removals by diminishing the degradation of the process, but also looking at some advanced emission control configurations. I also want to make sure you understand that the CO2 capture process with amines has evolved since 1930 with improved solvents and improved process flow sheets. So I'm going to give you a bit of a background and history of CO2 capture with amines, but first, I've taken a figure from the 2023 International Energy Agency update. This is a 23 update, references data back to 2010. And this is the total amount of CO2 capture projects that were in the pipeline by year. And the bottom line is by 2023, last year, they reference as much as 400 projects that are either operating all the way through to concept and feasibility. And I reference this, I want this figure up there because I want to make sure you understand that we look at this and we say, we really need to de-risk this process and understand the barriers to commercialization because there are a lot of plans for this technology to be used for point source CO2 capture. So this is a figure taken directly from a 1930 patent by Robert Roger Bottoms, and it was for sour gas treating or sweetening of sour gases. This would be natural gas, produced gases with H2S and CO2. I'm going to use the pointer here. I'm not going to use a pointer online, so the folks online won't be able to follow quite as well, but we have an absorber column, and to the right, we have a stripper column. And in the middle, we have a heat exchanger. We bring natural gas in, and we remove H2S and CO2 by running that flue gas countercurrent to amine through that column. This is an absorber column that runs at about 750 psig. It's a trade column, kind of old gas separation technology. And it's usually going to have about a 2-foot diameter and be a fairly large column. On the stripper side, we strip off the CO2 at high temperature by introducing steam in a reboiler at about 45 psig. This is, once again, the patented process, the old process. It would run at about 5 to 15 psig and also be a trade column. And you take that H2S and CO2 and you vent it in the rendition of this process. Now we have, if you will, co-opted this process for our purposes for CO2 capture. We bring flue gas in, it's going to have oxygen and it's going to have CO2. For a natural gas combined cycle, it might have 4 to 4.5% by volume CO2. It's going to run at about 1 bar, not 750 psig. It's going to be as much as 40 by 40 foot in rectangular configuration, a very large column. And we're going to send, it's notes here sweetened gas. This is just the flue gas with about 90% CO2 removed. On the stripper side, we run about 2 to 8 bar. That has random packing, whereas the absorber has structured packing. I'll show you an example of that. That's a kind of a key upgrade that we look at now for gas separations. The reboiler is going to take medium pressure steam, and if you can, from a power plant, and that's what we call that parasitic load. You'll find out that in our feed study that we concluded in 2022, being able to derate the plant by pulling steam or extracting steam was not possible. So we go with a separate supply of steam. And then the other key difference is CO2 goes to EOR, or enhanced oil recovery, or sequestration. So what are the issues associated with this process? In the first generation for CO2 capture, the absorber sizes are 20 to 50 times as big as that absorber for the original gas sweetening process. You have greater volumes because you have lower pressures and you have large volumes of flue gas. You need more packing to separate CO2 from the flue gas. At absorber pressures, it's a larger diameter column, more CAPEX for these absorbers. Energy use is important. For a power plant retrofit, the CO2 capture could pull as much as 15 to 40% from the steam cycle from the power plant. And the alternative is a new package boiler, but that's going to add CAPEX, as you'll see. We're going to have flue gases that have oxygen and NO2, and we know that those two components will oxidize our amine. They'll oxidize other amines, but I'm going to show you an example of how we study that. That will cause oxidation of the amine and corrosion, and then we have to do CO2 compression to introduce the CO2 to a pipeline to take it for EOR purposes or sequestration. So this is our process. So this is what we call the pizzazz process. It uses 30 weight percent piperazine. It's a cyclic diamine. So this is an upgrade. We call this a second generation process to the original rendition of the absorber stripper system. We have an absorber column and we have a stripper column. We bring flue gas in, we countercurrently contact, the flue gas travels upward, amine comes in, travels downward, reacts with the CO2. It goes out, we call this rich amine because it's rich in CO2, comes over, we go through a series of bypasses and as many as 3 heat exchangers. So we have heat integration that we think is advanced over the original rendition of the process using just 1 heat exchanger. We come over to a stripper. Now point out that as much as 70% of the rich amine in our process goes into the top of the stripper. The remainder goes in the bottom of the stripper after going through a steam heater. This is where we introduce heat to the process. This is what we call our heat duty. This is the biggest input in terms of heat to this process. We then strip off the CO2. It's a classic thermal swing process. We reverse the reaction. The CO2 comes off, goes through a condenser, off to a compressor, not shown on this diagram, and then to EOR or sequestration. We have what we call lean amine. It comes back through the cross exchangers and over to our absorber column. And before I depart this diagram, I want to point out one other thing. We have something called pump around intercooling. This is another advanced process flow sheet configuration. This improves CO2 mass transfer in this absorber column over that standard configuration where we simply have countercurrent flow. So I mentioned the packing. I mentioned we have trays in the 1930 patent in the absorber and the stripper. The diagram, the photo on the left are actual, these are called bubble trays. They exist at the Pickle Research Center. I took this picture 2 weeks ago. This might be something in a gas separation column. It has a large pressure drop throughout the column. So that's one negative against it. It also has less CO2 mass transfer per unit volume. So we've gone, and the industry in general has gone to something called packing, in this case, structured packing. You can see you're going to get surface roughness, which enhances liquid turbulence, improves the wetted area, improves mass transfer per unit volume, lowers the pressure drop through our column so we can use smaller induced draft fans, and it allows for smaller columns. It lowers CAPEX. So this is one very good example of a process or a mechanical improvement. So I mentioned in the 2 slides ago, the heat duty in the steam reboiler. This is a plot of heat duty in gigajoules per metric ton of CO2 removed for various solvents that have been developed over the years, starting in the 1980s. So think of this as sort of first generation CO2 capture. And this would typically be monoethanolamine, and we're going to be around 4.2 to 4.3 gigajoules per metric ton of CO2 removed. The industry in general has gone to advanced solvents, different chemistry, different amines that improve the process. Example is MHI's KS1 solvent. We drop that down to about 3.2 to 3.3 gigajoules. Through improved process flow sheets, MHI has their process improvements. We've been able, the industry's gone down to somewhere between 2 and 2.5 gigajoules per metric ton of CO2 captured. CanSolve's DC-103 is a very good example of a solvent that's out there in industry being used, and it's around 2.3. The UT Pizzazz solvent, that's piperazine. It's a cyclic diamine. It's a stable solvent that's very fast. It has good kinetics for reaction with CO2 in the absorber column. We have an advanced process flow sheet with those amine bypasses I mentioned, as well as absorber intercooling, which improves mass transfer. So we're competitive over here. And quite honestly, those numbers are probably, there's not much difference between ours and theirs. So to put this in perspective, from our feed study done at the Mustang station, that was a 460 megawatt NGCC. The capture over the course of a year at a 52% load factor would be about 1.6 million metric tons of CO2 if this plant were built. So let me back up and state, we did a full front-end engineering design, and we have a package that a developer or an investor could come along and build that plant. To date, that has not happened. So this is an engineering study. The plant is not actually operational. Nevertheless, our capture rate would be about 0.4 metric tons of CO2 per megawatt hour of generation. That heat duty, if you extended that out over the course of the year, would be about 3.8 million gigajoules per year. That heat duty represents about 14% of the plant fuel requirement to actually operate that plant in its gas turbines. And finally, the power requirement for the other equipment associated with the process, these are pumps, fans, and compressors, comes to about 14 megawatts. Not trivial, it's around 3% of the plant power. So let's get to some of those barriers and risks to CO2 capture with the means. And I first want to talk about the costs, and in particular, the capital costs. And I'm going to reference that front-end engineering design study. It was done on our host site, which is Mustang Station in Denver City, Texas. It's a 460 megawatt NGCC. There were 2 NGCC trains in aggregate between the two, about 460. They dispatched to the Southwest Power Pool, not ERCOT. There's a lot of available undeveloped land out there, so this is a good thing and actually can be a bad thing, and you'll see why I say that. It's in the Permian Basin. In fact, the site's 1 mile from a CO2 pipeline taking CO2 to EOR fields, so it's fortuitous in that regard. And then finally, a very important factor is because it's West Texas, there were less than 23 inches of annual rainfall. The plant itself uses groundwater, the power plant does. This is a constrained resource, and we were told from the very beginning that groundwater was not available to us for some of our cooling duties. So let's look at some key project decisions. We went with 2 parallel process trains, and the idea there is to match the dispatch of the 2 power trains. This also allowed offsite fabrication of the larger pieces of equipment at smaller scale so that they could then be hauled over the road to the site. If you build 1 process train, the strippers and some of the larger pieces of equipment are simply going to be too big to fabricate offsite for cheaper. So this was a good decision. Smaller heat exchangers were chosen because at the time of the study, the kickoff, natural gas was selling for about $2 per million BTU. And by the time we got a year into the project, it was up to $8 per million BTU. I will tell you now, fast forward to today, our decision to go with smaller heat exchanger and higher heat duty looks like a smart one, because in the Permian, we have stranded nat gas and it's trading negative as of last week. Elsewhere, it's trading around $2 to $3 per million BTU. But the bottom line is this is a classic trade-off. Do you go with larger heat exchangers, lower your heat duty, or in fact, go with smaller heat exchangers, lower your CAPEX, and just pay the hit on the natural gas? Because steam extraction from the power plant was not possible, they simply weren't in a position to be able to derate their plant. We went with packaged boilers for our steam for the regeneration side of the process over on the reboiler on the stripper. And then finally, because water was unavailable, we went with dry air cooling equipment, which was very large. If I showed you a site configuration, you see the size of these things are humongous, and it added a lot of CAPEX. So this is a little bit of a divergence from the CAPEX. I'll get back to the CAPEX, but I know that this is a question I'm going to get, so I'm going to go ahead and try and cover it now. This is the cost of CO2 capture in dollars per metric ton of CO2 from our feed study. And it's over a range of internal rates of return, or so we go from 0 out to about 10. And when we kicked off the project, the Southwest Power Pool was seeing more and more renewables come online. So we started out with a load factor assumption of around 80 to 85%. But by the time we got about a year or two into this project, in fact, the load factor, a realistic load factor for the NGCCs was about 52%. So this essentially lowered the amount of time that those NGCCs would be feeding CO2 to the CO2 capture plant. In fact, in March of 2022, there was as much as 90% renewables were feeding into the Southwest Power Pool. During that same year, on average, it was about 41%. So this really changed the economics of the project. If you look at an IRR of 10 and an 85% load factor, you're going to be somewhere around 105 to 110 bucks per metric ton of CO2. But in fact, it's probably more like 165 to 170 dollars per metric ton of CO2. Now, if you can afford a lower internal rate of return, you can actually lower that. But nevertheless, at any realistic number, it's going to be above $100 per metric ton CO2. So now I'm going to get back to the capital and trying to understand what drove those costs. And this is a tabulation of something we call total overnight costs. So if you said, Fred, build me a plant, have it running in 24 hours. So I have to build a plant. I have to design it. I've got to spec it. I got to get costs, and I got to put everything together and build a plant by tomorrow. That's what total overnight costs refers to. Those are today's costs. And these are, by the way, 2022 costs. So this is a tabulation. And for the most part, the total directs were about 385. That included all the large capital cost items. The total was about 725 million for a 460 megawatt power plant. So that largely is driving these costs. Let's break that down a little more. Let's look at the individual cost centers, the large capital items from large to small, starting with those air cooling systems that I alluded to. They're huge. They represent about 91 million in capital. But the next one down are the absorbers at about 37 million. And we have some control, having modeled absorber performance in the chemical engineering, in the chemistry department under Dr. Rochelle. We can actually try and improve the design of that. So let's look at that. What can we do with the capital costs associated with the absorbers? Can we reduce the size of those? This is the actual diagram from our EPC in the feed study report. Our EPC was AECOM. This thing is, it's basically we have two of these. They're 40 by 47 foot rectangular stainless steel absorber columns. They have two absorber beds and one water wash bed. They have intercooling, pump around intercooling, as I noted, and they have total packing height of 35 feet. But the total column height is 170 feet. And this size and the packing is sufficient for 90% CO2 capture on average when this plant's running. And so the question is, why is the packing's only 35 feet out of 117? That's where all the CO2 mass transfer takes place. Can't we shorten this column and get the same performance and lower our CAPEX? And so we're talking about bringing this absorber bed down. And actually, this is our flue gas ducting inlet. And the question was asked, and our EPC went off and did some CFD. And they came back and they said, yeah, we can do that, but not by much. And at a cost to maldistribution of the flue gas in the bottom packing section. And that's evidenced by different colors. If you have uniform coloration, that means uniform gas velocity going up through the packing, and you get uniform distribution, and you get optimal mass transfer of CO2 into your amine. So we can do that, but we actually shorten this zone and we kind of mess up the fluid dynamics, the gas fluid flow dynamics, and we get maldistribution. So this is a classic example where rigorous design principles drive certain things that you simply can't get around when you're building these plants. So other considerations driving CAPEX. And I put this table up for two reasons. And one is because in retrospect, we said, maybe there's some things we could have done different on the Mustang station feed. But it's also a good way to think about maybe Mustang Station wasn't located in Denver City, Texas. What if it's located closer to the coast or to a river where you have access to surface water for cooling duties, and you have other things that are not constraining your project? Or perhaps you don't have as much area. So we went and we considered each of these. Air cooling systems, maybe we could go with water cooling. Now, I'm not going to put a number to it, but these are things we can consider. We could go with carbon steel in the absorbers because these things are very large. And maybe we can accept carbon steel and the amount of corrosion we have over its lifetime. You know, we had a lot of available land, and we thought at times that maybe our EPC was using too much of it and increasing the ductwork and piping and increasing the cost of those things. So can we shorten the ductwork by going to a tighter configuration? Solvent reclaiming, I'll talk briefly at the end about that. Maybe we could go with a turnkey service instead of having a $20 million installation, a permanent installation on site. The power plant said you cannot do steam extraction. This was something that other feeds around the nation have looked at. Some of them can do steam extraction, but generally speaking, you're going to find that the power plant's not willing to derate their plant, so steam extraction is not possible. And then finally, solvent heat exchangers. Maybe we should go with larger heat exchangers, and that trade-off actually has benefits going the other direction because you can make smaller some of the other process units in the plant. So let's move on to another barrier or risk to the process, and that's amine losses and mitigation methods associated with those losses. And a couple of years ago, we started putting together a table from the published literature of solvent makeup rates. And these are in kilograms of solvent per metric ton of CO2 captured. And I've kind of shaded out because I don't want to focus on other solvent developers. But I just want to point out that we have a range of rates, but all the processes have to have some solvent makeup. And this is from degradation, it's from emissions, perhaps it's just from not tight operations. But in general, we find that piperazine around 0.5 kilograms of piperazine made up per unit metric ton of CO2 over the course of the operation of the process. And we're somewhere in the low to middle range of that range. But the bottom line is the takeaway you should get is that all these solvents actually experience some form of degradation. How can we mitigate that? We studied that at a pilot scale at a couple of places. One is at the Separations Research Program out at the Pickle Research Center of UT. That's where I reside. And then actually at the National Carbon Capture Center in Wilsonville, Alabama. This is the process flow sheet again. I'm not going to go through it in too much detail, other than to point out we bring flue gas in. It's going to have impurities. It's going to have as much as 13% oxygen. And this is very different from that original gas sweetening process from 1930. That oxygen will oxidize amines. We know that. We've studied that in the lab on a number of occasions, and we can run pilot plants and we can determine the rates. And that is imparted as dissolved oxygen, we call DO, or it can be entrained oxygen bubbles that travel downstream in the process. We've studied stripping the DO out with nitrogen sparging in the absorber sump. Think of this as intercepting that oxygen as early as you can, stripping it out before the solvent goes to the hotter side of the process. We know that these reactions will accelerate as the solvent gets hotter. The other impurity is NO2, and it can be as much as 2 to 5 ppm. It doesn't take much NO2 to react with the amine and cause oxidation processes. It's the same thing. It comes in, the flue gas comes in with the flue gas, contacts the amine and the absorber packing in the sump and causes that oxidation. And we can pre-scrub that upstream before the flue gas ever gets to the absorber. And we do that with sulfite and thiosulfate. The chemistry is not something I want to get into today. But in essence, we convert that to nitrite, drops out in the pre-scrubber train, flue gas passes on. We can remove as much as 90% of the NO2 and diminish the rate of oxidation of the solvent. So I don't know how much chemistry you guys remember, and I'm not going to get into a lot of chemistry, but what we do when we run these campaigns is we collect daily samples. We ran our campaign at the National Carbon Capture Center as much as 6,000 hours. And each day we collect liquid samples, we collect gas phase samples, but when we collect those liquid samples, we run a number of analyses at UT and elsewhere. And one of those, I'm not going to get into all of them, is we look for amino acids. So piperazine itself will oxidize to form, this is just two examples of amino acids that we'll see in oxidized piperazine. There's several plotted here. They're in millimoles per kilogram over the course of time throughout our campaign. And before I move on, there's a theme here. You'll see this in another slide or two. You see colored background, and each of these different colorations represents a step change in our oxidation mitigation methodology. So we start out, we're pre-scrubbing out the NO2, we're stripping out the DO and the absorber, and we're actually running a carbon bed to adsorb out impurities. And then each step, as we change the color, we remove a mitigation method, and we see these amino acids start to accrue in concentration. This white background, we have no mitigation methods online. We see these amino acids going up. The gray here, we bring those mitigation methods back online. We have some strange things happening, which makes my life interesting. Things go down and things accelerate. And then finally, you see a precipitous drop. And that's where we implemented reclaiming, a process called solvent reclaiming. I'll talk more about that in a moment. But the bottom line is, we look at these parameters, these species, as well as other things with other instrumentation that resides at the Pickle. And in aggregate, we see around 30 to 75% reduction in the oxidation rate with our various mitigation methods. So we can mitigate the oxidation. So let's talk about what that means in terms of emissions through gas phase monitoring data we collected at the National Carbon Capture Center. I've shown the process flow sheet again, but I've added one thing, which is a separate water wash column. So most of these systems are going to have a water wash capability. And what that is the flue gas goes up, travels up, the amine travels down. The flue gas, we've removed 90% of the CO2, but there's some degradation that happens. And so we get degradation, volatile degradation species go out, and we go to a wash tower, a separate wash tower, where we can, think of this as emission control, where we can wash out some of those species that are formed in the process. And in fact, we get some piperazine there, the parent amine itself. We measure in the gas phase here and here on the outlet to the wash tower, and we want to know what the trends look like there. So doing that, we use an instrument called an FTIR, and we can measure ammonia. These are the ammonia data in part per million plotted over the course of that same campaign out almost 6,000 hours. And we see the ammonia in the gas phase starts out around 2 to 3 part per million, starts going up as we take our mitigation methods offline. We're starting to degrade our solvent, and we're starting to see ammonia. Ammonia is an oxidation product of piperazine. You would see this with monoethanolamine. You'd see this with a lot of other amines. And then at some point, with no mitigation methods, it goes up. And then finally, we bring those methods back online to see if we can abate the emission. And in fact, we do. And then I alluded to, there's some strange things happening late in the campaign that make our life interesting. And we start to see that the ammonia goes up in a sort of unmitigated fashion. We implement reclaiming, we drop that back down. Okay, so can we mitigate ammonia emissions? This is the absorber column only. I'm showing the process configuration without the stripper and the heat integration. It's the absorber, and it's that separate wash tower that I alluded to. So the flue gas goes in the absorber, goes up, travels through the wash tower. And one of the things we can do, we can run several different configurations at the National Carbon Capture Center, and we did just that. You'll see that in a tabulation of data in a moment. But we can convert that to an acid wash. It's a dilute sulfuric acid wash. And when we do that, we actually react the ammonia that's evolved with the sulfuric acid to form ammonium sulfate and prevent those emissions of ammonia. This is a tabulation of data collected with an instrument called a PTR-TOF mass spec. And it's data measured on the gas phase outlet location I depicted with the blue dot 2 slides ago. And I have this tabulated by different water wash configurations. And there are 2 species here. We measured several species. I've only listed 2 for the sake of time. One is ammonia. Now, mind you, these are in part per billion. And these are acetaldehyde in part per billion. Now we have a class of compounds that the EPA calls hazardous air pollutants, or HAPs. And acetaldehyde is one of those. And this was a species that we are particularly interested in understanding, where we're going to see much in the way of acetaldehyde coming off our process late into our campaign. And we got a very fortuitous result. In fact, it's never more than about 50 part per billion. We thought it might be higher. But the interesting thing is, the water wash configurations really don't affect this number. It's typically going to be somewhere around 35 to 50. But you can see with the ammonia, using our conventional water wash, we're at 7.5 part per million, or 7,400 ppb, upwards to 25 part per million late in our campaign. It was only when we implemented that acid wash that I mentioned that we bring that number down. And boy, did we bring it down. It was 10 ppb with our acid wash. So this is very good evidence that, in fact, we can utilize advanced water wash configurations to control, in this case, ammonia. So I've alluded to solvent reclaiming on a couple of occasions, and this is a little bit in the weeds, and this isn't really the central focus, but in fact, it actually had a significant impact on our thinking at the end of this campaign. So what is that? So we come up to the plant, we actually brought a turnkey offsite process. It was a single stage thermal reclaimer. Think of it as single stage distillation unit. And we bring a slipstream of solvent off to that unit. It goes through this single stage thermal reclaimer, and then we return solvent. Late in our campaign, the solvent looked like this. Well, I can assure you, it started out looking like this and maybe like that. But when we started reclaiming, that's what our solvent looked like. And so we don't put too much stock in the coloration of the solvent, because all these solvents start to change color as we degrade them. But it is a good visual for understanding, do we have a fairly well degraded solvent? So as we started our reclaiming process, that's what our solvent looked like. The product coming off the reclaimer was back to clear liquid, looked like water. This is essentially 30% weight piperazine. And then the solvent inventory, after processing 3 inventories through that process, looked back like this. And so, you can look at that, and the visual is it worked. But what we really want to know is, did it change the chemistry of the process, and did it change emissions? And so now I've put up the ammonia plot in part per million again over the course of this campaign. You saw this earlier. We can see the mitigation methods are taken offline, and we bring them back online, and then they go back up. But at some point, they're going up in a sort of unmitigated fashion. And it was only when we implemented that single stage thermal reclaiming process that we brought down the ammonia emissions and the oxidation of the solvent to something very similar to what we saw at the beginning of the campaign. So this confirmed to us that most likely any commercial version of this type of process or this plant is going to have some form of reclaiming, whether be it on-site, a permanent installation, or a turnkey process that's brought and implemented on a semi-routine basis. I'm going to finish with my top conclusions, which I started with. So the barriers to deployment include the cost of the process. We're looking at about $168 per metric ton of CO2 removed from our feed study completed in 2022. This was largely driven by high CAPEX. Amine losses can be partially mitigated through flue gas impurity removal. This is things like oxygen and NO2. And emissions are also impacted by that very same thing. They can be partially mitigated through reduced solvent degradation and through those advanced emission controls. I showed you how we implemented an acid wash to control the ammonia emissions. And if nothing else, realize that the process, folks really started working on this, I'd say in the late 70s and 80s, to think of it as a CO2 capture process, that was typically for CO2 for other purposes, not for sequestration. But when they did, they started with solvents like monoethanolamine. We've improved on that with second generation solvents. There's a European open source solvent called Caesar 1, similar to piperazine in some ways. And actually, those solvents really are advanced over MEA. But we also have advanced process flow sheets, which lower the heat duty of the process, lower the energy requirement. So I'm going to acknowledge the Department of Energy who funded the FEED study, and they funded the pilot campaigns that I've referenced. Dr. Gary Rochelle's research group, I got my PhD under Dr. Gary Rochelle, and I actually work with him at the Pickle Research Center. The Texas Carbon Management is our consortium of 17 different industrial sponsors who sponsor a lot of our work. The Separations Research Program and Dr. Frank Seibert ran our SRP campaign that concluded in 2022. The Center for Energy and Environmental Resources, we sort of reside in that center at the EME building at the Pickle Research Center. The National Carbon Capture Center in Wilsonville, Alabama. And then we've received partial funding from ExxonMobil and Honeywell UOP for some of the data you saw today. And then finally, AECOM was our feed for the EPC for our feed study. And I will take any questions you might have.
All right, let's thank our speaker. All right, any initial questions in the room? I think I had one to maybe get us started. So, yeah, to some degree, you mentioned the size of these absorbers and strippers. I think you said in your feed study, 117 feet tall and
correct.
Yeah. So and there's large diameter. Is the size of this diameter and height, is that driven? Let's just think about a power plant capturing CO2 from a power plant. Is that driven? Which dimension is driven by the size of the power plant? Is it both dimensions, like the diameter and the height, or is it mostly one or the other? If we're thinking about, if we're sticking these somewhere where we know power plants are, just to try to imagine what the footprint is.
Yeah. So not so much the height driven by the flue gas volume. The flue gas volume drives the diameter. And the flue gas volume is so much higher because we're at lower pressures, as well as the fact that think of a 460 megawatt power plant. You're going to have a lot of flue gas being introduced to these absorbers. The height is driven by the CO2 capture need, or the amount of flue gases, the amount of CO2 that you need to remove from the flue gas. So typically we think of 90% as sort of a minimum. If we redid this feed study, our basis would probably be 95 to 97% CO2 removal. And in fact, we might have to go with more packing, slightly taller tower, absorber column.
All right, I'm gonna go to one question online, then one here in the room. So question online, what would be the value of having inline monitoring for the different types of analysis and tracking of chemical products that you've shown, or where are the biggest gaps in online monitoring? I think you're doing little individual samples every hour or every day and things like this. Exactly.
Okay, so I'll repeat the question. So what's the value of having online monitoring throughout the, so I'll think of it, we'll talk about it in two contexts. First is in a pilot campaign, and the second is in a commercial plant. And the value would be great. And in fact, one elements or one set of data that you were not able to see today because of a time constraint, if I had 15 more minutes, I'd love to get into it, is we did online monitoring for things like dissolved oxygen. And that's because we were removing dissolved oxygen and we wanted to know how effective it was. And in fact, we come to find out that online monitoring of the liquid phase dissolved oxygen can give you a good indicator of the health of the solvent at any given point in time. And we could see that trend to where the solvent was at a more oxidized state. So that's in the liquid phase. We also implement online monitoring with an FTIR instrument of the gas phase. That is something that pretty much every study, every pilot campaign does, that either use that PTR TOF mass spec technology, or they're going to use an FTIR or some other technology in real time to look at the emissions coming off the plant. So there's a lot of value in online monitoring. And I would expect that if I was a plant owner, I would expect that to be an element of the design.
Thank you for sharing your time and insights. We appreciate it. When you look at the $168,
Yeah.
is that mitigated further by being able to sell the CO2? How much would that be able to be sold for per ton for EOR? And then also, are there 45Q or 45B tax credits that just got passed with the Inflation Reduction Act or some other act that also might help reduce that cost?
Absolutely. So that's a very good question. Another kind of aspect of what we do that I wasn't able to discuss. And in fact, we're not policy guys, we're engineers, we're chemical engineers at that. And so we don't necessarily work on the economics with respect to 45Q. But what you allude to, and I'll just kind of make sure other folks know, is that you can get a tax credit. Now it's $85 per metric ton of CO2 captured of available CO2 captured and sequestered, or $60 per metric ton of CO2 captured and delivered for EOR purposes. And that absolutely improves the economics, but it doesn't cover it entirely. And when we go to conferences, we hear about that from the industry folks in the crowd. They say, yeah, but we're still not going to close that gap, even at $85. But it's a far cry from what 45Q was until I think it was the BIL passed it, increased it in 2022. So it's actually, it does improve the economics, and it's going to be essential to any implementation from what we see.
Fred, thanks for your time. My question is, I'm assuming that load factor is the same as capacity factor?
So I don't know if that translates entirely even, because I'm not sure if you take into account downtime for maintenance in one versus the other. I think they do, and I'm not sure exactly how that goes.
Yeah, I mean, if you annualize capacity factor, it should take into account downtime.
Yeah.
I'm just sort of curious because 52% is pretty low. I mean, if you're at ERCOT, it's closer to 68 to 70%.
Right.
So if you were to move that Denver City plant up to Plains, you'd be in the ERCOT service area, and that's just like about 30 miles north.
Yeah.
I mean, you saw that cost curve drop pretty quickly if
Yeah.
you were able to increase the capacity factor. I mean, that would help a lot, I would think, just to kind of make the economics work.
Yes.
Is that something that your EPC looked at, or I'm not sure why Denver City was chosen? Maybe it was an existing plant and you had power line capacity out there, or was it?
Yeah. So good question. So let me point out. So it's really interesting because if you look at a map of the Southwest Power Pool, I expect somebody's going to pull it up on their phone. It's a really interesting dynamic because they pick up a little sliver of far west Texas, and then it goes all the way up to the border with Canada. It goes through Arkansas and Oklahoma, Iowa, Kansas. It's really strange that far west Texas is not part of ERCOT. And so there's that. And absolutely, yeah, maybe if your plant is located somewhere else and you're not competing with as much renewables, it would improve the economics. The second question is, well, how do we choose our plant? Well, in 2019 and 2020, when we were looking for a host site, it wasn't that easy to find one. But Mustang Station was receptive to this study. So largely, you'll find that the FEED studies were done by plants and operations that were receptive to understanding what this looked like. So if you could show me another plant that was interested in a FEED study 5 years ago, if there was another plant, perhaps we would have chosen it. And perhaps if it didn't have the groundwater constraint, it would have improved the economics in terms of the CAPEX. So there are a lot of things, and geography probably would have affected that. I don't know if it would have brought it down to the range of $85 a ton for sequestration purposes. Yeah.
Is there a way you can use produced water to help cool? Or is it just, would it need to be cleaned up so much that it would be a net negative?
I suppose, but the first thing I think when I think of produced waters is produced waters are not, it's not a produced water with 500 TDS. It's going to have a lot of TDS. It's probably going to be off-gassing things. It's probably not going to be the kind of spec of water that you're going to want to run through a plant for cooling duties. You're probably going to have a lot of cleanup for that. Secondly, it's going to have to be a really consistent supply. You don't want to have to wait for a produced water supply in order to kick the plant online. So I think there's probably some supply constraints as well as quality constraints that are going to affect that.
All right, quick follow-up online. We'll go to another one in the room, and I don't know if you have this off the top of your head. I suppose the question is about your FEED study, 460 megawatt natural gas plant. What is the rate or volume of CO2 captured that would be delivered in a pipeline?
Yeah, so I put in the table, that little box. I think it's 1.6 million. Let's get there. 1.6 million metric tons of CO2 per year at a 52% load factor. So I think that's the number the person's looking for.
Right, sounds good. All right, question in the room?
Yeah, thank you, Dr. King, and thank you, Dr. Kosman, for the
Sure.
presentation. So my name is Bim. I'm from Indonesia. So I have two questions. The first one is quite superficial and technical. You mentioned about solvent reclaiming. So is it just pure chemical reclaiming, or do you use some kind of thermal reclaiming and also physical reclaiming? And the second one is, I'm a geologist by training, and my concern is more about the purity of the carbon. So how pure it is, the carbon has to be before it's injected to the geological formation, because if there are some kind of the chemical outside carbon, it's gonna affect the longevity of the geological formation, right? So how pure it is, it has to be before it's get injected.
Yeah.
So yeah.
Okay. I will answer the second question first. There's two answers that come to mind on that. And that is, how pure does the CO2 need to be for sequestration purposes, I believe. So we have a spec of less than 10 part per million oxygen, which we measured in our recent National Carbon Capture Center campaign. That was sort of an open question. And the second one is 95% CO2 or greater. So there are other impurities that I think we would probably look to make sure that they're low enough. But I'm not really sure off the top of my head what those look like. I do know those two we met. Okay, so then back to the first question, and that is, what was the nature, what was the physical step you did for solvent reclaiming? So what we did is we did this single stage thermal reclaiming. Think of it as a single stage distillation cut, kind of a rough cut, not a particularly sophisticated thing. And it was actually a first of its kind for piperazine. That is not the only type of reclaiming available in the marketplace. There's also ion exchange that's done. And if you go into a refinery where these plants are processing processed gas in a refinery, there's ion exchange beds running these different solvents over them. But in our case, it was a single stage thermal reclaimer. And if we were to design something a little more advanced, it would probably be a little more sophisticated than that.
Okay, there's another question online. I'm not sure if you'll know it because there's an acronym that I, of course, don't know. Does TCMP have or develop or are in the process of developing a modeling tool that could significantly enhance efficiency of the CO2 conditioning process? I'm not sure if you even know.
Does
TCMP
TCMP
Yeah,
have a model for
significantly enhancing efficiency of CO2 and CO2 conditioning? That makes sense. I don't know how to interpret it, so maybe it's an unclear question. We'll go to the next one.
I don't know
Yeah.
what that is.
The next one here, I'm not sure if there's another one in the room here, but this is kind of your, maybe we'll end on this one. It's kind of your pie in the sky. You show sort of some cost trends there, and you've gone over several factors, at least in the CO2 capture process for these particular solvents. But you know, what kind of do you expect is the limit, or how will we understand the limit to how much we can reduce the cost, I suppose, is one question, but you know, reduce the heat need for the processes. Now I remember one question I had. It's related. which is, you said in your feed study of the natural gas power plant, the design was to bring in a separate boiler.
Yep.
And are you capturing the CO2 from that boiler also? Are you boiling with natural gas, I perhaps assume?
Yeah, yeah.
So anyway, what are the limits to this kind of technology? And we'll go
So
there.
I'm also going to answer your second
Yeah, yeah,
question
you can do
first.
that one
So
first.
we brought in a package boiler for the steam supply because power plant wouldn't let us do steam extraction. And to my surprise, yes, we designed to capture the CO2 off that, and you can get the 45Q tax credit on that CO2 for that purpose. So yes, in fact, you capture that CO2. And if you look at the economics of a plant and you're generating, you have a revenue generation through sale of CO2 for EOR or for sequestration purposes. Well, you would sell for EOR. You can get dollar for EOR, but you can also get tax credit for either of those. So it improves the economics if you actually do capture that CO2. So back to your first question, which is, what do I foresee in terms of being able to reduce the cost of the process? So when we look at the best way to answer this is to say all 400 of those plants in 2023 are developed and built, and we've got another 800 that come online in the next 5 years. And therefore, all of a sudden you're driving this demand, and you can look at this and say, well, that's going to drive down the cost because you start to have full scale implementation. And you can look at a lot of scenarios out there, different analogies, different technologies. Maybe EVs is one, EV cars. We're not sure that really is going to take place in this place. And the reason being, one reason that I'm going to cite is that the technology's been around since 1930. It's not a brand new technology. It's a technology that we've been chipping away at for many, many years. And there are limits to how much you can do to diminish an absorber size. And so you're going to have a certain amount of CAPEX that you cannot diminish. And that was part of this exercise. There are certain things you can do to do what we call a technology intensification. But there's also the possibility that when you go to build your plant and they're building their plant and they're building their plant and so on, all of a sudden structured packing becomes an unavailable resource and the price goes sky high. So this could go a different direction. It could actually increase that supply constraint, could increase the cost of the technology. So we just don't really know. But if you asked me, are we going to be at 10% of the price of the cost that we are today, 10 years from now, because of commercialization of the technology, I'd say there's no way. It could come down some, but it isn't going to come down in a dramatic way like that.
All right. Well, we'll end there. Let's thank our speaker, Dr. Fred Fossman, Research Associate in the Department of Chemical Engineering. Thank you very much, Fred.
Okay.